Hello, everybody. Welcome to the Veni, Vidi, Vici attacks on ETW blind EDRs presentation by the Binary team. Event tracing for Windows, or ETW, is one of the Windows technologies that provides support for various security tools and EDR solutions. However, attacks on this technology can blind the whole class of security solutions that rely on telemetry from ETW. This topic is very important for all the experts dealing with Windows security, malware detection, and incident response. Binary is a firmware security startup focused on detecting threat originating below the operating system in the firmware and understand how they moved up the stack into the OS kernel and userland to deploy the next stage components. One such component can implement an attack on ETW to disable or send bogus events to the OS level sensors. As we'll see through this presentation, there are plenty of attacks to pick from. I'm Claudiu Teodorescu, CTO and co-founder of Binary. Thanks to Matt Greiber, I have a nickname, and as you can see, you can use it to call me by my last name. I have great expertise in digital forensic, reverse engineering, malware and program analysis, to name a few. I've been instructor for special topics of malware analysis at Black Hat, speaker at multiple security conferences, first time speaking at Black Hat.
I'm Igor Korkin. I'm just a Windows security guy who is always looking for new challenges and discovering new attacks on Windows kernel and find the ways to prevent them. My blog is here. Please continue.
Also, meet Andrey, Red Plate Golchikov, an expert in Windows internals and Windows security. He has more than 20 years experience researching low-level operating system internals. Unfortunately, Andrey lost the coin toss and he will sit out this presentation. Agenda. Modern Windows-based endpoint detection and response solutions, EDRs, leverage ETW to detect and mitigate cyber threats and computer issues. Researchers are finding ways to disable ETW, and it's of critical importance given that these attacks can blind a whole set of EDR solutions that focus and rely on ETW for visibility into host events. Even more important is researching and developing ways to detect if ETW has been tampered with and notify the security solutions in place. We'll start our presentation by going over the architecture and features of ETW. Next, we'll touch on the current state of ETW research, both in cybersecurity and academic space. We'll switch our attention to attacks on ETW to blind security solutions. We'll go over the published methods of disabling ETW and introduce two new attacks that blind Process Monitor and Windows Defender. Last but not the least, we'll introduce ETW Check and Memory Ranger, two solutions that can reveal and prevent attacks on ETW. Now, a little bit about event tracing for Windows, what it is and what are its components. Event tracing for Windows, or shortly ETW, is a built-in Windows logging mechanism designed to observe and analyze application behavior. ETW was introduced quite a while ago in Windows XP as a framework implemented in the kernel to troubleshoot OS components' behavior and performance issues. Since then, it has been expanded and improved significantly. For example, in Windows 11, ETW can produce more than 50,000 different event types coming from around 1,000 ETW providers. ETW has the following advantages. It's available system-wide in all recent Windows operating systems without having to be installed, loading a kernel driver, or OS rebooting. Supports a standardized framework to produce and consume logging events, and also supports high-speed logging and lets application consume events in real time or coming from a disk file. Let's focus a little bit on the ETW framework and its three distinct components. First, the controllers, which are applications that can enable providers and control the lifespan of a session. Then providers, which are applications that contain event tracing instrumentation and produce events if enabled by a controller. And consumers, which are applications that select one or more event tracing sessions as a source for events. They can receive events stored in the log files or from sessions that send events in real time. ETW is used to collect events in large-scale business solutions, such as Docker or Amazon CloudWatch, Microsoft SQL Server has been using ETW for more than 10 years. ETW providers. As you can see in the picture, there are a myriad of OS components that are supplying ETW events, from applications, services, DLLs, to OS kernel components and drivers. I'll not go into details. Everybody can recognize in this table multiple core components of the Windows operating system. Using ETW for malware hunting. One of the first examples of using ETW tools to reveal and analyze malicious behavior was presented by Mark Rusinovich in his talk Malware Hunting with SIS Internal Tools about 10 years ago. Since then, developers of modern EDRs have leveraged ETW to monitor security-related events and successfully detect and respond to cutting-edge malware. SIS Internal Tool Process Monitor is leveraging ETW for network tracing. Its latest version still relies on ETW for such visibility. We'll demonstrate attack on ETW on Process Monitor in a demo, and technical details will be provided as well a little bit later. Also, Network Shell and Packet Monitor Windows tools provide network troubleshooting diagnostic and packet sniffer functionalities using ETW providers such as Microsoft Windows NDIS Packet Capture and Microsoft Windows PKTMon. ETW has become a common signal provider for EDR and antivirus solutions to reveal malicious activity. And in 2021, there are more than 10 leading market EDR solutions that use ETW for threat hunting. ETW is on Twitter, from Alex Lonexu providing insight into how to build an EDR based on Microsoft Threat Intelligence ETW provider, Matt Graber creating a dynamic analysis tool based on ETW for fun, Nazreddin informing us how Symantec uses ETW to detect malicious activity, or Robert demonstrating his EDR tool based on ETW at this year's Black Hat Europe Arsenal. There are plenty of practical research projects demonstrating the ability of ETW to capture malicious activity and perform threat research and reverse engineering. For example, Zach Brown in his DERBICOM presentation showcased how ETW helps Office 365 red teams to answer forensic questions such as who's the user that launched the evil process and where the data has been exfiltrated to. To monitor DNS resolutions, the author is leveraging Microsoft Windows DNS client ETW provider. Also, DARPA has sponsored several ETW-based monitoring systems for malware detection. The project Windows Low-Level System Monitoring Data Collection obtains data from many ETW providers, including from the anti-kernel logger session, to reveal and reconstruct various attacks like browse exploits and malicious file downloads. Project Marple focuses on hardening enterprise security by automating the detection of APT threats. One of its modules, Holmes, collects host telemetry using ETW to produce detection signals for APT campaigns. Also, APT Shell project uses ETW for logging system call routines. This scheme helps detecting remote access Trojans by analyzing malicious behavior such as key logging, screen grabbing, remote shell, audio recording, and the registry key manipulation. MITRE also developed an ETW-based security sensor. Security experts from MITRE built a custom ETW-based sensor to detect process injection, capture process creation and termination, file creation or deletion with the help of ETW providers. Research for ERNW, contracted by German Federal Office for Information Security as part of the Sisyphus project, performed the technical analysis of Windows 10 logging capabilities, providing insights on how ETW helps Windows telemetry capturing. ETW is also in academic papers. ETW is a hot topic in academic media. Papers focused mostly on detecting malicious behavior. Some examples include malware characterization using behavioral components from George Mason University, detecting fileless malicious behavior of .NET C2 agents using ETW from University of Amsterdam, or tactical provenance analysis for EDRs from University of Illinois. According to MITRE CVE database, in 2021, there is an exponential rise in the number of ETW-related vulnerabilities that receive the CVE number. So it is safe to assume that ETW has caught the attention of bug hunters. ETW is helpful for defenses, but it has drawbacks. Let's look a little bit into that. One of the most important drawbacks is that ETW being released to be as an internal tool at the beginning has an opaque structure, including undocumented providers and providers that issue undocumented events. ETW event templates are stored into the PE resource section under WEBT_template resource ID. Also, ETW can be used and leveraged by living of the land malware because it provides sniffer functionality for file and registry operations, process, thread, and network activity. Also, it can provide keylogging functionality. Since events can be logged to disk in log files, ETW can float the hard drive in a DDoS attack. Also, malware can use ETW to detect sandbox detonations. And some ETW providers are only available in PPL processes, but malware can disable PPL for targeted processes via kernel mode driver without causing BSOD. And next, disable the hidden ETW providers. ETW can be bypassed. Ways to disable ETW logging are widely discussed on Twitter, from passing a true Boolean parameter into ETWP stop trace kernel function, to finding an ETW specific structure and dynamically modifying it, or patching ETW event write userland API to return immediately, thus stopping the user mode loggers. Let's look next at some malware examples that are using ETW to evade detection. So in March 2018, Kaspersky released a report on Slingshot, a complex and unknown cyber espionage platform targeting African and Middle East countries. Slingshot, the first stage loader, renames the ETW logs by appending .tmp extension to avoid leaving traces of its activity. Minisling, a module in the platform, uses Microsoft Windows Kernel General ETW provider to obtain the last reboot time, and Microsoft Windows Kernel Power ETW provider to obtain the last unsuccessful attempt to shut down the machine. In 2019, LockerGoga ransomware implemented functionality to disable ETW by turning off the signals from Microsoft Windows WMI activity ETW provider via WEBT util tool. In August 2021, Trend Micro researchers published the details of a new campaign from APT41 targeting South China Sea countries. The researchers mentioned the use of two shellcode launchers that can run payloads, uninstall themselves, disable ETW to evade detection, and also try out credentials. In terms of post-exploitation frameworks to disable or bypass ETW, we can mention Sharpsploit, disable ETW monitoring for current process, Scarecrow, payload creation framework to bypass EDRs, an EDR evasion, which has around 10 examples of blocking ETW locking. In 2020, MITRE ATT&CK framework has introduced the indicator blocking and disable cloud logs sub-techniques to impair defenses technique to describe attacks that maliciously redirect or disable host-based sensors, ETW included. Now let's focus on the big picture of ETW attacks. As can be seen in the diagram, there are 5 types of attacks, each designated by a different color, targeting each component of the ETW architecture. Red shows attacks on ETW from inside an evil process. Light blue shows attacks on ETW by modifying the environment variables, registry, and log files. Orange shows attacks on user mode ETW providers. Dark blue shows attacks on kernel mode ETW providers. And purple shows attacks on ETW sessions. Next, Igor will go over each type and later introduce and demo 2 brand new attacks on ETW.
Thank you very much. It's my turn. Let me briefly describe attacks on ETW inside the evil process. As we mentioned before, ETW providers can be loaded in process memory as DLLs, which implement logging events using event write routine. Attackers can modify the control flow so that the events won't be logged. Look at the numbers 1, 3, and 5. Attackers can directly patch the ETW providers functions which supply events, see number 2. Attackers can send the bogus events by calling event write function. Finally, attackers can modify the internal structure such as process environment block. As a result, the fake process image file will be locked. We can specify one more vector of attacks, which includes modifying ETW environment variables, ETW registry settings, and log files. Attackers can disable ETW for .NET applications by zeroing ETW environment variables using CMD or registry, see number 1. We have revealed that some ETW providers save their settings in registry, and these ETW providers can be disabled by patching the registry keys, see number 2. Finally, attackers can manipulate with ETW log files to hide their footprints, see number 3. Attackers app can disable ETW providers running in other user mode processes. Attackers can disable ETW provider globally by locating the corresponding ETW data structures such as ETW handles, trace levels, and zeroing their values, see number 1. Attackers can disable ETW providers for the target processes using 3 approaches: by patching ETW data, see numbers 2, 3, and 4, by patching ETW functions responsible for logging events, see numbers 5, 6, and 7, by calling functions to unregister and disable ETW providers, as well as terminate ETW threads, see numbers 8, 9, 10, and 11. Finally, malware can block logging only for specific events without stopping provider completely, see number 7. This helps to hide the attack on ETW. Another class of attacks bypasses ETW providers using kernel mode driver. Attackers can disable ETW by locating kernel handles and modifying the corresponding data structures, see numbers 1, 2, 3, and 4. Another example of globally disabling ETW is hooking in trace event, see number 6. Here the author leverages Infinity Hook, which works well on all Windows versions from 7 to 10, but due to updates, it won't work on used Windows releases. Finally, attackers can call custom syscalls, which doesn't include ETW instrumentation, and information about this call won't be logged. The final class of attacks is focusing on ETW sessions. Attacker can stop and start ETW sessions using ETW API as well as built-in tools. See number 1 and 2. Attacker can remove or disable providers from active sessions. See number 3. Finally, attackers can patch the kernel data structures in order to change their configurations. See numbers 7, 8, and 9. Today, we will use these techniques to show you 2 attacks on ETW. Let's summarize attacks on ETW. All in all, there are 36 different techniques to disable and bypass ETW, and this number is likely to increase. Some more details about ETW sessions. The number of running ETW sessions is limited. The default maximum number of simultaneously running sessions is 64. Users cannot run more sessions than this number. The NT kernel supports a maximum of 8 system logging sessions with fixed session names. One of them is NT kernel logger session. It collects various internal events, and it is very helpful for EDRs. However, users aren't able to start the NT kernel logger session twice, so they need to stop the previously session first before trying another command variation. This is a key point for the attack. As an example, we will look at Process Monitor, which uses absolutely the same technology as many EDRs. Process Monitor is free and very popular for malware analysis. We choose Process Monitor to be neutral. Process Monitor launches an ETW session to receive network events. We have revealed that Process Monitor version up to 3.60 use NT kernel logger. Newly issued Process Monitor version 3.85 uses session called procmontrace. This is the way how Process Monitor receives network events. Attackers can stop the running session using session names and start fake ones. As a result, Process Monitor stops receiving network events. Even relaunching Process Monitor doesn't help to continue collecting events. Let me show you how it works. Okay, let me briefly explain you how ETW hijacker works. First, it stops the target session and starts its own with the same name. Then it checks the status of the created session. If the malware session has been terminated, it repeats from the beginning. As long as the malware session is active, malware sleeps for a few seconds and then checks the malware session is still active. Let me briefly tell you about ETW check. It is a powerful tool developed by Red Plate to extract various kernel data. Here you can see bits of information that can be gained and an example of output fragment with VMI logger contexts. Now let's move on to the secure ETW session running by Windows Defender. Windows Defender uses two ETW sessions, Defender API logger and Defender audit logger. Both of them are running on a startup as an auto logger, so they can be disabled by modifying the startup setting located in registry. Each ETW session has a security descriptor which is located in registry. Here you can see the value of security descriptor for Defender API logger from registry and dumped from the corresponding kernel structure. By patching these values, you can change the security descriptor. Now, let's move on querying information about secure ETW sessions. Windows provides query all trace W API to get information about ETW. After calling this function, the control goes to the kernel and finally to the ETWP query trace. In the right, you can see the pseudocode of this function. The function includes several security checks that prevent returning information about this session. First, it checks access rights by comparing access security descriptor and process token. Second, it checks whether the session is marked as security and implemented one more check based on PPL mechanism. By default, users cannot query info about Defender ETW sessions because they're running with high privilege with enabled security trace. Both these parameters are located in the VMI logger context structure. These data values are read for each call of this function. So, malware can load its driver to patch the values inside the target VMI logger context structure so that the function will always return information about this ETW session. To query information about secure ETW session, malware driver has to patch security descriptor and clear security trace flag. Now, let's move on to stopping secure ETW sessions. Windows provides stop trace API to terminate a running session. After calling this function, the control goes to the kernel and finally to the ETWP stop trace. In the right, you can see pseudocode of this function. The function includes several security checks that prevent stopping the session. First, it checks whether the session can be stopped until stopped using internal flag. Second, it checks access rights by comparing session security descriptor and process token. By default, users cannot stop Defender ETY sessions because they're running with high privilege and are not stoppable. Both these parameters are also located in VMI logger context structure. These data values are read for each call of this function. So, malware can load its driver to patch these values inside the target VMI logger context structure so that the function will always call the function ETWP stop logger instance, which terminates the session without additional security checks. To stop secure ETW session, malware driver has to patch both security scripter and logger mode. Here is the summary of both attacks. To query information about the target's secure ETW session and stop it, malware driver has to patch 3 fields in the corresponding my logger content structure in memory. Let me show you how it works. So, Windows Patch Guard is a software protection utility designed to forbid the kernel from being patched in order to prevent rootkit infections. However, we can see that Patch Guard doesn't protect kernel ETW structures from illegal write access. This is crucial. To deal with this issue, we can use Memoranger, which is a hypervisor-based utility that are designed to prevent attacks on kernel memory. After loading, Memoranger allocates a default enclave for the OS and previously loaded drivers. Memoranger traps loading ETW blind driver and moves it to the isolated kernel enclave in runtime with different memory access restrictions. Using EPT, Memoranger can trap access to the sensitive data and foist the fake null data to the attacker instead of the real one. Memoranger is a proof of concept that can be customized for solving various security tasks. Let me show you how it works. So, operating system is protected. ETW was originally designed to perform software diagnostics, and nowadays it is widely used by various EDRs and cybersecurity solutions. It is crucial to understand the attacks on ETW because these attacks can disable the whole class of security solutions. ETW includes some design issues which makes it possible to bypass it. We've presented a new tool called ETW check that can detect ETW attacks. Memoranger can be customized to prevent patching sensitive kernel ETW data. Claudiu, can I ask you to go on, please?
As a conclusion to conclusion, I want to leave the audience with a possible scenario. Let's assume that an attack originates in the firmware, says persistence, executes the next stage payload to move up in the kernel where it can implement one of the attacks showcased in this presentation. This will be devastating due to its stealthiness and resilience to OS reinstallation and hard drive replacing. That's why today, security solutions must receive signals from below and above the operating system to be able to respond effectively to such threats. Thank you, and see you next time.